Live? All right. Good morning, and my name is Steve Marr. I'm with Risk Management Professionals, and welcome to our continuing webinar series on the application of safety environmental management systems to offshore facilities. We're going to be doing this as part of a webinar presentation. We're using a WebEx interface, and the good and bad parts of that, it does allow for two-way communication, but we're going to have to keep you on mute because during the course of the presentation, activities on your end, shuffling of papers, phone calls, and the like, we don't want to have that interrupt the presenter or interfere with the listening for the other participants. This is part of our ongoing series to take, as all of you are aware, the Risk Management Professionals does a lot of work in the process safety risk management arena, and also spend a lot of time with safety and environmental management programs for offshore facilities. So this is part of our ongoing series to share that knowledge, that background, and provide a platform for people to apply their SEMS programs to their offshore facilities. Another key logistical item, this will be primarily a presentation. At the end, there will be an opportunity for question and answer, and you'll have the opportunity to be presenting that via audio if you'd like, or you can present a question in a chat window that will get a message to our webcast producer, Nicole Otramba. At the very end, there will be a QA session. Carlos will address any questions. And also, if you'd like to, the video in the upper right-hand corner of the screen can be extended by just grabbing the corner of that. So without further ado, I'd like to introduce our main speaker this morning, Carlos Cheek. He's got a bachelor's and master's in mechanical engineering, has been involved in the application of SEMP and SEMS to offshore facilities, and he'll be focusing on a key element of the SEMS program, safety and environmental information, and trying to share with you a little bit of information on that, key things to look out for, how to build a program, and deficiencies, and also implementation tips. So Carlos?
All right, thank you, Steve. As Steve said, I'll be discussing safety and environmental information, some common deficiencies, and also some implementation tips. Some quick background, this is part of the SEMS program that was just implemented last November as part of 30 CFR 250 and specifically subpart S. This is referencing back to the earlier revision of API RP 75, and specifically for safety and environmental information, API RP 14J is very important, and we'll be talking about that as well. Basically, the quick purpose of SEMS is it's to document, it's the body of work to show that you are maintaining and operating your facility in a safe manner. Safety and environmental information in particular is the details of the equipment in that process, and each piece of equipment, how it's detailed, how it's lined up. This also ensures that management is dedicating the proper resources needed to prevent an accidental release, such as training, equipment maintenance, and also personnel necessary to maintain the system and operate the system in a safe manner. Some of the key topics I'll be talking about today for safety and environmental information. I'll go over some general documentation requirements, some ideas, some things that I've seen out there at the platform so far. I'll be talking about P&IDs specifically, and then I'll talk about some details for relief valve sizing, filling densities, and we'll talk about electrical classification, ventilation. And I'll finish up with some measuring effectiveness, just some ideas we have as people are developing these programs to see how these programs are indeed working at the facility and some things to look out for. So this is a broad description of safety and environmental information, all the things that can be included in, and should be included in there as well. And we'll be touching on most all of these and trying to get a game plan together for places you can try to find this information or ways to try to start to get it and start to compile it in a single place, in a single location, so that if you are ever audited or whatnot, you can pull this up and say, this is exactly where we meet these requirements, because this wording is straight out of the regulations. So we typically recommend, hey, if it says, electrical area classification, then you have a section that says, this is my electrical area classification, this is how it's taken care of, and this is how we as a facility are meeting that regulation, that requirement. Quickly, safety environmental information versus process safety information. This is a SEMS comparing to the onshore version PSM. They're very, very similar. There's not much difference. And the main reason for that is simply because this section, this information, this body of information, is mainly driven by the requirements of the HAZOP, or the hazard analysis, or onshore it's the process hazard analysis, and also the complexity of the system. So it's important when you do your hazard analysis that you have this body of information available to you so you can make those informed decisions on how your system is going to respond, how your system is working, what's actually out there in the field, what sort of pipes do you actually have, that sort of thing, the actual chemicals that are going to be running through there. Some common deficiencies that I've seen so far, the biggest one is simply most facilities have most of the information. It's out there on the platform, or back at the corporate office or somewhere, but it's not compiled. There's not a one place where you can go to get that information, and that's very important for this program, especially because the next step then is this has to be easily accessible to all personnel at the facility. Any mechanics, maintenance, they need to be able to go to it, access it, look up some information, when they're trying to do their job, and if it's not all in one common place, then they can't do that. And it doesn't all have to be all in a single binder. It can simply have one place where you can reference it. So for this, it's documented that so-and-so is responsible for this task. They have the most updated version. They're in charge of that. But it's documented in this. You can go find it. Okay, and then you can go straight to there. So there's no wandering around, asking, that sort of stuff. The next thing is piping and instrumentation diagrams. P&IDs, it's tough to keep up with P&IDs as things change. For some reason, there's usually a red-line version, a master copy that they keep on site and things like that. But there needs to be, updated CAD drawings. Those need to be kept up to date with, especially for the hazard analysis, just so you can have that information, what's actually out there. Safe upper and lower operating limits, we'll talk about that. Very important, just in general, and also relief system design tends to not be discussed as much. It's hard to find exactly where those calculations were made, and we'll give some examples for that as well. Some quick places to start. Just to kind of get the rough cut, the low-hanging fruit, as I like to call it. Upper and lower limits are readily available to most facilities. Just going up to the control room operators, and you can go through the screenshots and you can get most of the upper and lower operating limits right there. The next place you look is the operator round sheets. People are checking these things, the compressors and all those stuff. They have to be run, and they're going to keep running in order to be able to run, so that they're going to check those things. And the information is somewhere in a sheet in some drawer somewhere, and you can just go find that and document that. And then also equipment manuals. Typically you have those equipment manuals somewhere on site. They're going to have the information in them of how those equipment needs to be run, and then you can just reference it there, or maybe copy and paste it quickly, and then that'll take care of that. Well control, alarm and shutdown descriptions. Typically facilities have instrument callouts where they do all those tests. Someone is responsible for that task of simply testing instrumentation and alarms. So they have a description of the whole facility, in some sort of format, and simply gathering that information from them and putting it in a format that someone else can understand, task done. It's kind of a low-hanging fruit. Someone's already doing it. Materials of construction, that should be on the P&ID, but if it's not, then you should be able to go straight to your equipment manuals. I'm going to start into P&IDs and some, show some examples of what should be on P&IDs, what's a better P&ID, and I'll actually go into some of the details of how actually to read a P&ID and that sort of stuff. This is the process flow diagram. This is the basic flow of the system that you can look at in a single sort of quick glance of what's going on there, the main flow line. The basic controls and sensing is a good start, but the PFD should also contain stream data, so inlet and outlet temperatures and pressures at certain locations would really, really help. And that's essentially your upper and lower operating limits. So the temperatures going into a certain set of exchangers, temperature coming out of those exchangers, pressure going into a separator, pressure going out of a separator. Obviously, temperatures and pressures in and out of heaters is also really important. And right there on the PFD can be a really useful place to put that. This is an example of a P&ID. Basically, for the vessels, it's important, so you see the depropanizer reflux accumulator. It's important to see the size, the material, max allowable working pressure, and that sort of information right on the P&ID is a really good place to have that information. You should also have maybe material that it's made out of, and then in the bottom right, it's an example of a PSV. Having the PSV information on the P&ID, the size of the PSV, the capacity of the PSV, and also the set point, all really helpful and really useful to have right there on the P&ID. I'm going to go into a little bit about instrumentation and how that's actually called out on the P&ID. An instrumentation loop is basically a control system. It's taking a value at some point, and it's trying to control the process, either flow or pressure, somewhere downstream or potentially upstream. The actual symbol for the instrumentation is important. The letters have a function identification, and the sequence, the tag number, is also important as well. And we'll talk about what that means, the actual symbol, the circle with the line and whatnot, and how that plays into each piece of instrumentation. Sensors and transmitters are the actual things that take the reading. This is the actual thing that's in the pipe, and it's measuring the flow or it's measuring the pressure, and the transmitter then sends it somewhere. So a flow element is a thing actually in the pipe measuring flow. A flow transmitter then sends that information somewhere else. And the same thing for a pressure transmitter or a thermocouple. And we'll talk about what the FE, FT, PT, that sort of stuff in nomenclature in just a second. Indicators and recorders. A flow indicator is simply just indicating the flow. It's a gauge, if you will, or maybe just a number on a screen is a flow indicator or a pressure indicator. So a pressure indicator can just be like a physical gauge just to go up to and look at, and or it could be just a number on a control panel. Whereas a transmitter actually sends a signal. So that's the difference between a pressure indicator and a pressure transmitter. Pressure transmitter is some sort of signal that you can then use, whereas an indicator is just a number that usually has to have manual, or the operator has to see to take to use that information. A controller is once it receives the signal, the controller then does something. The controller has some sort of logic involved in it, and it says, okay, this is high, this is low, and then it's going to take action. It's going to close something or open something based on the signal it's receiving, typically from a transmitter. So as we said before, the actual symbol itself actually makes a difference on what that actually means. Discrete instruments are things like the actual indicator, a DCS or distributed control system that will actually go and do something, and the PLC, that's when you actually have control and you can change that, and that actually takes action for you. So, and those are the symbols that are actually used on the P&ID. This is a nomenclature. It's a lot of information, but essentially it tells you there's a letter. Each letter stands for a certain either process measurement or element type. So for, say, flow, you're going to get F. And then for indicator, you're going to get I. So FI indicates a flow indicator, whereas P, pressure, and controller is C, pressure controller. A control valve is CV, so PCV is a pressure control valve. This is just a basic table. This changes slightly from facility to facility based on something that they have going on at their individual facility. But this is just a general breakdown and a general idea of instrument nomenclature. And this is just another set of, you have switches and alarms. Alarm low is AL, and pressure is P, so pressure alarm low, PAL. And it's basically the same idea. This is just a small example of an instrument loop. FE, the flow element, is the actual piece of the actual instrument in the pipe that's measuring flow. That sends some sort of information to the flow transmitter. The flow transmitter then sends an electrical signal to the controller. The controller then has logic involved. It says this is high, this is low, and you can program the controller to then close the valve or open the valve based on how much flow you need. And the FV is the flow valve that's based on the flow controller. So this is a small loop based on how much flow is in there. The flow element is going to tell the flow valve to open or closed. And this is just a more, just another example of a loop where the level transmitter, LT1, is telling the level control valve, LCV1, to open and close based on the level in that vessel. So as the level gets higher or lower, LT1 is going to tell LCV1 to open or close. And that's an instrument control loop. Closing out P&IDs, this is just some basic equipment that you'll see on P&IDs, especially oil and gas. You'll see accumulators, separators, reactors. These are all just vessels. And there's very different symbols depending on the different facility and then how the P&IDs are drawn. And I just wanted to give you some examples. You see a heater, a heat exchanger, some pumps, and a basic vessel there. Cause and effect diagrams are a really good tool to have to use in conjunction with your P&IDs during the HAZOP, especially for complex facilities or complex processes that have a lot of interlocks. A cause and effect diagram essentially shows the interlocks that are connected with any sort of piece of instrument or instrument controller. I have a quick example. I'm not sure how well you can read that, but if you take the PowerPoint, you can zoom in on your own. But basically, you can see that when that pump shuts down, it then also closes the valve, the inlet valve, and it also shuts down the upstream flow. So that's an interlock for when that cause happens. The effect is you close the upstream and downstream flow. So then in your HAZOP, you can use that information to say, oh, when this actually closes, we have these interlocks in place. So these are our safeguards that we know are going to happen. And it's all organized and right there for you. So you can use it and reference it really easily. This is just a site map. Site maps are also very important to see where things are, how things relate to each other, especially good for human factors and things like that. It's just good to be able to see that stuff and reference it easily. So it's good to have a site map available as well. Electrical one-line diagrams. Usually it helps to see where things are getting their power from. It's just a quick demo or electrical diagram showing where things get their power. Relief valve sizing. This is based on API 521. This is the fire case for relief valves. You can basically, this equation in a nutshell relates W, the required relief capacity of the relief valve, to the temperature of the working gas, the temperature of the potential fire around it, also the molecular weight of the chemical that's in there, and the normal operating temperature of the gas. So all of those factors combined will tell you the required relief capacity of that vessel. And it's fairly simple to work out. You have some basic, temperatures and pressures in your system that you have, and you also know the molecular weight of your components going through there. So you can work through this pretty quickly, and if you have no current justification for the sizing of your relief valves, you can set this up in Excel and whatnot and just kind of work through this, chip away at it, and take care of it. So it's there, and you can basically reference it. Filling densities. This is based on 29 CFR 1910, and it's basically describing how much you can fill any given vessel. So filling density is the ratio of weight of the gas to the weight of water. And based on the specific gravity of whatever you have in there, so for example, propane, it tells you what the filling density you can use. And I'll have a quick example in the next slide, basically showing that if you have a propane storage tank, it's marked for 30,000 gallon water capacity. How much can you fill that tank per regulations, per 29 CFR 1910? And the answer to that is you use the table. You can see that propane with a specific gravity, you have a filling density of 41 or 44. So then you simply take the weight of the water, you convert that to pounds, max weight of the gas, 44% filling density, and then you're able to convert that and show that you can fill the tank to 88%. So when the gauge on the side of the tank says 88% full, that is your max that you can fill that vessel based on the regulations. So if you have any sort of question on how much you can fill a certain vessel or not, you can reference this to show that you're in regulations and that you're using the right requirements. Also, you can reference NFPA 58, section 7423. Electrical classification. This is a tough one for some facilities. Most people know it, but they don't know exactly why. So basically, a class 1 facility is a location where flammable gases are present. That's a given. Class 1 Div 1 is ignitable concentrations of gases exist under normal circumstances. So that means that under typical normal circumstances, you're going to have some sort of flammable gas in the atmosphere. And the examples that are typically given are vents on tanks that potentially are very sensitive, so they will relieve gas to the atmosphere. Now, usually the question is like, well, the vent is actually a safeguard from overpressuring the vessel. And the way it works is if it's actually going to initiate that safeguard fairly often, then you have to count that as the normal. Even though it's not the recommended operating, it's the actual normal operating. So typically vents, another one is maintenance. When you're doing maintenance on certain vessels or certain tanks and whatnot, depending on how the maintenance is done, it could be a class 1 Div 1 area while that maintenance is going on. Class 1 Div 2 is that ignitable concentrations may be present, but they're normally confined. So the normal operating is that all the gases are confined. And these are abbreviated recommendations as well. You can reference API 500 to get the actual details on there. Unclassified is when there's basically no possible way for gases to escape. This is basically long pipelines. When there's long sections of pipe with no valves or gaskets or anything like that, you can call that an unclassified section of your facility. Ventilation plays into what the classification for your section is. If you have the proper ventilation or adequate ventilation, as we'll describe here in a second, you can then call it a class 1 Div 2 section, even if there are potentially some ignitable gases in the area. For naturally ventilated enclosed areas, according to API 500 section 6, you can use this equation which essentially relates area, A, to the volume of the building, and the temperatures of the gases inside, or the temperature of the air inside the building, and the temperature of the air outside the building, to determine the number of air exchanges that you need and the area of the inlet and outlet of the building to see if you have the proper air exchanges that you need. For another way you can have adequate ventilation is if essentially an outdoor facility, and the way they describe outdoor facility is if walls are only 50% of the possible height. So basically the walls don't go all the way up to the ceiling, or only 50% of the possible height that they could go up. Or if they have neither a floor or a ceiling, so if there's no floor, basically a grating, and then no ceiling, then that's also adequate ventilation. And then if they have no ceiling and the walls go up 25, or there's no walls for 25% of the perimeter. So those are three ways that you can classify an outdoor facility and have adequate ventilation and be a Class 1 Div 2 location or area. I was going to talk about API 14C safe charts because those are an important thing to have in your safety and environmental information. Basically, the safe chart is a prescriptive recommendations for safety devices that need to be put on certain pieces of equipment. This is just one example. This is just a regular pressure vessel, and it basically lists the safety devices that should be on any general pressure vessel. It also goes through pumps, compressors, all the main pieces of equipment, heat exchangers. And you basically then take these safety devices and you put them in a safe chart or a safety analysis function evaluation chart, safe chart. And you basically list all the safety devices and then what their action is. So down there in the left column, you have the actual service, the actual equipment, and you see the safety devices all listed out. So the example is the suction scrubber, and it lists all of them, PSH, PSV, LSH, LSL. And then on the right, you then see the actual function that it actually does. And you'll see there that it actually shuts down the flow when you hit the PSH. So the pressure switch high will actually shut down the flow going into the suction scrubber. So you get a real quick, all-in-one place glimpse of everything that's going to happen or all of the safety devices that are on your equipment. So it's a really useful tool, especially in a HAZOP. You can reference it really quickly and have that information at your fingertips. I was going to do a quick, just sort of description of how to measure program effectiveness or ways that you can, as you're developing your program, see how it's working for you. There tends to be a lot of, or some confusion over personnel safety versus process safety. Personnel safety is essentially slip, trips, and falls, and process safety is something totally different. And relating personal safety to how well your process safety is actually working there's very little correlation there. So the correlation that we make is it's relating airline baggage handling injuries to airplane crashes. You know, the two you just can't really measure one with the other. Essentially, personnel safety indicators are lost time injury statistics. You know, how many first aid injuries, lost time injuries, things like that. Process safety indicators are a little bit tougher to get to. Sometimes they're not necessarily reported, or they're written up as maintenance work orders, or as a near miss that no one really said anything about. They just kind of fixed it just as normal operations, and they just kind of keep working on it. That's just the way the process keeps, the way the plant runs. And I see a lot of that sometimes when they're just used to it and they just take action and they do it and whatnot. But really, they shouldn't have to be using safety devices in that way. We'll just go to the next slide. You'll see things like an operator knows he has to go drain off a vessel. he's basically stationed there. You know, every so often he has to go open a valve and drain the liquid out of the bottom of it. That's a process safety indicator that, you know, that's something's going on there. Either there shouldn't be that much liquid going in there, or the process isn't designed properly, and you need to have some sort of, you know, automatic way to get the liquid out of there. Because if that operator isn't able to then respond and drain that liquid as often as he does, you're going to get some sort of, you know, injury, some sort of, or not necessarily injury, but something's going to happen when that liquid carries over. Another one you see a lot is they're regulating the flow using a bypass. So you have a control valve of some sort, then you have a bypass around it, and they're actually using the bypass as a typical or normal operating stance. And that's another process safety indicator, like, hey, you know, there's something going on there. We need to look at this control valve, you know, really make this work, because they shouldn't be, if you have the control valve, you shouldn't need to use the bypass valve necessarily. Also relief valves, obviously. If relief valves are lifting on a, you know, continual basis or often, or they're simply using the relief valve in a normal way, it's like, oh, every time we shut down, we just, you know, pop the relief valve. You know, that's another process safety indicator. Hey, you know, relief valves are a safety device, and they shouldn't necessarily be lifting that often. So, you know, maybe we can do something to fix that. Emergency shutdown devices, ESDs. Those, anytime you're using an ESD, that's a near miss. A lot of these are near miss incidents that need to be reported as using an incident investigation procedure. Corrosion rates and also fouling of equipment. These are all process safety indicators that need to be looked at to say, hey, our process isn't running like it should. So we need to take a look at that and take action. It's basically anytime you have a deviation from the design intent of the piece of equipment or the system. That's something that you need to look at, and it's a potential gap for you to fill. And in all, I mean, it's a lot of work. The safety and environmental information, there's a lot of pieces, and they're usually scattered all over the place. But just with a little bit of hunting around and you're really trying to get in there, you can pull it all together, and it needs to be all in one compiled document that you can then make available to your whole facility. And that's about it. I'm going to go ahead and open up to questions.
Maybe the best thing to do is
we have some questions from the audience.
Oh, okay. I think that's the question. Okay, I'll help out here a little bit. Is the mic working? Is the mic working, Nicole? Yes. Okay, great. One of the questions that came from the audience are cause and effect diagrams required for safety and environmental information. Do you want to go ahead and take a first cut at it and elaborate? Okay. One of the things that for a lot of offshore facilities, am I on the camera now? Okay, this is better. One of the things for offshore facilities that seems to work pretty well and accomplish a lot of these objectives are safe charts. Safe charts have been kind of a mainstay throughout the SEM program, formulated originally in some of the early versions of 14C, and also referenced in API Recommended Practice 75. And cause and effect diagrams are basically another flavor or version of that. And the basic idea is some sort of matrix or correlation between the key protection systems, their functions, what activates them, and what happens to the end devices. And so those of, whether you're looking at facilities and engineering contractors that refer to them as cause and effect diagrams that bring those things into play, or you're looking at safe charts, you're trying to correlate a lot of those key interfaces between what activates key protection features and what the effects are. Did you want to add to that? Okay, cool. And the other question is same for sitemaps? Okay. Do you want to start with that? Or?
Yeah.
Okay. All right. Yeah, one of the things, I think it's on your list, Carlos, is basically the overall configuration of a platform or some sort of offshore facility. If you're looking at onshore facilities, a site layout diagram, where key equipment is, especially key safety equipment, gas detectors, fire extinguishing devices, and other protection features. You want to know where those are during an emergency. It's also very important during the design of the facility. So whether you're looking at an onshore facility and you're looking at process safety information that requires a site layout drawing with a lot of these key safety features and emergency response equipment in it, or you're looking at an offshore facility where you're looking at a platform and some detailed diagrams for where this equipment is, you're really trying to accomplish the same function. Identify from a design perspective what's there and what you need, and for an emergency response, make sure it's readily available. And I think, by the way, guys, those are very good questions. I think that really tends to amplify the overall theme of where Carlos is going with this, which is the close correlation between a lot of the reasons why you have process safety information for your process safety management program and why it's so important for the SEMS program to have safety and environmental information, which, again, that close correlation also emphasizes the fact that the offshore facility operators have a lot of resources internally and people who probably have a lot of knowledge on how to compile this, how to do it efficiently, and how to effectively roll it out for your SEMS program. Did you want to add to that? No? Okay. All right, Nicole, any other questions? All right. Oh, you know, maybe I'll highlight a little bit. I'll just put my own spin a little bit on the importance of this safety and environmental information. All of us here, one of the things that risk management professionals we do a lot, or we get called in to do a lot, are the hazard analysis and actually rolling out techniques such as HAZID, HAZOP, JSAs, etc. One of the real things that can really bog that down is the deficiencies, as Carlos was highlighting, of inaccurate process flow diagrams, P&IDs, etc. Whenever you've got holes in those, whenever they're incomplete, it really tends to make that other part of the SEMS program, the hazard analysis especially, and of course other elements too, but especially the hazard analysis, very difficult to do, very time consuming, very wasteful in many cases. And so good quality safety and environmental information can go a long way towards efficient implementation of the program and saving a lot of the money that you're going to be spending putting the SEMS program together. Okay. Did you have any other points you want to highlight? Okay. All right. Did you want to close it out?
And I guess if there's no more questions, we thank you for tuning in, and we will see you again. When's our next seminar?
Good question, Mary. Yeah. All right. Thanks. Good question, and I'm glad you asked. On March 8th, we actually were very privileged to have been invited to do a paper at the 7th Global Congress on Process Safety. Carlos Cheek and Esther Brawley were co-authors on that, and I'm one of the authors on it too, where we tried to put a paper together that really helped emphasize and show this flow of accidents, major accidents that have caused paradigm changes in the regulatory perspective on process safety, yielding process safety management from incidents that happened in the 80s to the Deepwater Horizon accident and the Macondo well release being a trigger point for really a shift in what was happening for offshore facilities, and trying to look at that, draw parallels to it. And another thing that I think will be really helpful is in that paper, if you don't have a copy, please go ahead and request one. You can request one from any of us here, call the phone number, send us an email or whatever, but it provides a very nice summary table at the end contrasting the differences between PSM and SEMS and the differences in all the various elements, and we go into a lot of detail. If you as offshore facility operators have arms of your business that are well studied and entrenched in process safety management, you can use those resources also to support your SEMS program. So anyhow, a lot of the stuff was in the paper, And we'll be rolling that out at the 7th Global Congress on Process Safety. And where I was going with that is on March 8th, next Tuesday at 10 a.m. Central Time, we're going to be providing an overview of that presentation, kind of a dry run for us, but I hope hopefully it'll benefit all the offshore facility operators who have to do SEMS programs, and we're going to be rolling all that out next Tuesday morning. Also, to keep in touch with things, if you want to know about future elements of our SEMS webinar series for offshore facilities, please go ahead and feel free to check our website, www.sems1.com/offshore webinars, one word, .html, or just call us at our main number, and we'll be happy to help you. Long answer to a short question. Anyhow, I'll just echo Carlos's thanks for tuning in, and please feel free to call us if you have any questions on the SEMS program. A lot of people have a lot of work to do over the next few months to meet their November 15th deadline. Feel free to call, and if we can help provide some tips or some training materials, or as you know, we're engineering consultants. We help people put SEMS programs together. Just let us know. Thank you.